Okay, so today we will continue our revision. So last lecture we stopped at so we're still doing single phase AC circuit revision, and we are at power in AC circuits. As you can see, we are almost done with the revision part. So most of the concepts and the theory revision we will finish it during today's lecture, and even we will solve a couple of examples. Next lecture, half of the lecture will be just doing examples similar to what we need in the upcoming chapters. And as we will see, if we look at or if we understand correctly the AC circuits, the next chapters will be much easier for us. Okay, so let's start with what we did last time, just a quick revision for basic concepts. We said in AC circuits that the voltage and the current will be waveforms. So assume this is a voltage V of t, and this is a current I of t. And as you can see that the voltage is a cos wave. It starts at peak, then it goes to zero, then peak, then zero. And the current is a cos wave, but this cos wave here is a little bit lag. So here is the peak of the current, here is the peak of the voltage, and as you can see that the current is lagging the voltage with number of degrees. And to get the power, what we need to do, we need to take the voltage and multiply it by the current at each time instant. This will give us this form, and this form is P of t. So here V of t equal to V max cos omega t, and I of t equal to I max cos omega t, but shifted with a delay phi. And shifted with certain amount of delay phi. Now if we multiply these two, this will give us the power P of t. So we can write down that P of t equal to V max cos omega t I max cos omega t minus phi. And we said this power, or this waveform, is a power waveform, which we called it the instantaneous power. So this is what is called the instantaneous power, and this is the physical power in your circuit, and this is what is the power actually flow in the circuit. But we did some simplification for this. Okay, just this simplification here, I did it using the sine voltage and sine current, and in our previous lecture we did it for cos voltage and cos current, just to prove that it doesn't matter what is the waveform for voltage or current, both are sinusoidal. So if it is a sine wave or if it is a cos wave, you treat it the same. Okay, so we did this proof last time for cos, and as we mentioned, I will never ask you for the deviations, but it's very important for you to understand what is going on, how they came up with these definitions, why they call this active power, why they call this reactive power, what is apparent power. You need to understand this, okay? That's why we do all these proofs. It seems useless in terms of I'm not asking to do the derivation, but I see it useful. You need to understand what is going on, not just take the final equation and use it. Okay, you need to understand the flow. So we reached up to this point with when P of t equal to the addition of two terms. This is the first term and this is the second term. So the first term has an average. This first term has an average. The second term has no average. So we named the first term here, we named this component as active component, and we named this component as reactive component, and if we add the active component to the reactive component, we will get the instantaneous power, and this is the power in the circuit. Okay, so these two powers, the active and reactive component, is just an projection or analysis. We analyze the power into two components, but what we have physically in the circuit, we have just P of T. Okay, so what we have in the physical circuit, we have P of T. Okay, but we analyze it into two components. Now let's have a look here. So what I did here, I took this wave, so I took this P of T, okay, using MATLAB, and I analyzed it using MATLAB into the two components. So this blue wave here is P of T. Then I analyzed this P of T into its two components. The first component here is the active component, and the second component here, this component, is the reactive component. So at any time instant, if you add the reactive component to the active component, if you do this point plus this point, it will give you this point. So the power P of T equal to the active component plus the reactive component at any time. Now if you look at the reactive component, okay, so if you look at the reactive component, you will see it has positive and negative, and the positive area equal to the negative area, which means it has no average. So the reactive component is positive and negative with zero average. The active component here is always positive. As you can see, it's always more than zero. Okay, so the active component here, the active component is always positive. Also, it has an average. Its average is not zero. Okay, so there is an average here. It has an average. The value of this average is V I cos phi, as we did last time. The value of this average is V I cos phi. If we go here, the value of the average, which is multiplied by 1, is V max I max over 2 cos phi, and we said that V max I max over 2 is V RMS I RMS. So the average power is V I cos phi. The maximum value of this wave here, the maximum of this wave, the maximum of the reactive component, if you look at the reactive component, its maximum here is, so it has a maximum of VI sin phi. So VI sin phi is the maximum of the reactive component. VI cos phi is the average of the active component. So the active component is a waveform which has some characteristics, and the reactive component is a waveform which has some characteristics. If you add the active component to the reactive component, this will give you the exact power in the circuit, or the physical power in the circuit, or the instantaneous power. The active component is always positive, so it's always consumed, so it is productive. It has an average, so there is an average consumption, or there is an energy consumption. The reactive component has zero average, no average, but it has a maximum value. And it is positive and negative, means it is going back and forth between the source and the load. That's why we call it reactive or interactive. So here we start to define P. So here we start to define P, okay? So P is called the active power, or sometimes we call it the real power, and this real power equal to VI cos phi. Please, please, please don't forget that P is a value. P is the average of the waveform. P is not vector. P has no angle. P is not function of time. Okay, so the active power is VI cos phi, or I write it as magnitude V, magnitude I, cos phi. I don't like to write it like this, magnitude V, magnitude I, because I'm assuming you understand what is P. I don't have to write that you use only the magnitudes. And this is one of the common mistakes. This is something that makes us upset when we are marking the exams. When we see students are calculating P and they are using magnitude and angle of the voltage and current. Okay, so this is a misconcept, okay? So please don't do this mistake, okay? So P is a scalar. It's a value. It is not a waveform. It doesn't have any angles. So P equal to VI cos phi. Note V and I are RMS. They are root mean square values, okay? And this is by default. So any given voltage will be RMS. So make sure that you are using the RMS value, and this is why when we move from time domain to frequency domain, we will convert into RMS, or we will divide by root 2. So P, or the active component, equal to magnitude V, magnitude I, cos phi. So what is the definition of phi? Phi is the angle of V minus the angle of I, or we can write it as angle of V minus angle of I, or we can write it as theta V minus theta I. So this is one of the important definition, that phi equal to theta V minus theta I. And we name phi as the phase angle. And we name phi as the phase angle. The second definition we have is Q, and Q equal to magnitude V, magnitude I, sine phi. Again, don't forget that V and I are in RMS. Don't forget that phi is the angle of the voltage minus the angle of the current in degree, which we call it the phase shift. Okay? And this is the second important equation we have. Don't worry about all these equations, okay? All these equations will be in the formula sheet. I will post the formula sheet for the midterm exam this week. I know that the exams or the midterm or quizzes, we cannot force a closed book policy, okay? So to have a fair chance, we will allow the exam to be open book, okay? If we cannot force a policy, let's make it general. Okay, so the exams will be open book. But I prefer to give my students a formula sheet even if the exam is open book, so I minimize the time you will waste to find the formula. So I will give you a formula sheet, you can use it during the exam even if the exam is open book. So Q equals to VI sine phi, and Q again is a scalar, and Q represent the maximum of the reactive component. That's why it's a single value. It is not a vector. It doesn't have any angles. And Q is the maximum of the reactive component, and this is an interactive power or interactive energy that goes between the source back and forth. Okay? Now, we know that P here, VI, this is, so this is P, VI cos phi, and this is Q, Vi sine phi. So to get your power P of t, you need to take P, which is a magnitude, and multiply it by a cos wave, and you need to take Q, which is a magnitude, and multiply it by a sine wave. And this sine wave has double the frequency of the source to get P of t. So we cannot say that the power we have equal to P plus Q. Okay, we cannot say this. Why? Because P and Q are not the same, are not from the same nature. So P is the magnitude or the average of a cos wave. Q is the maximum of a sine wave. So we cannot just add the magnitudes together. We need to consider P to be cos, and we need to consider Q to be sine. And we know that the difference between sine and cos is 90 degrees. So to add P and Q, we need to add J, or we need to add 90 degrees. And when we add P plus JQ, we will get a power that we name it S vector, and it is vector because it's a wave, it has magnitude and angle, and we name this power as complex power, and we name this as reactive power. So Q, or the reactive power, it is the maximum of the reactive component, which is the interactive energy between the source and the load. P, or the active component, it is the average of the active component, which is the positive power that goes only from the source to the load, and this is a productive component. The complex power is the power you have in your circuit, which has magnitude and angle because it's a waveform. How you get the complex power? By adding P plus JQ. Don't forget that P is a number, Q is a number, they are constant, they are scalar, there is no magnitude and angle. Only S vector is the one that has a magnitude and angle, that's why we call it complex power. Now in terms of units, the unit for P, as you can see, P is volt ampere or volt current. Q is volt ampere, volt current. S is P plus JQ, which is volt ampere. So the unit for P, Q, and S, it is the same unit, volt ampere, which is confusing. To avoid any confusion, they decided to give each term a different name. So for P, we name it the volt ampere as watt. So the unit watt is used only for P. For Q, we name it's a volt ampere as volt ampere reactive, or VAR. So VAR is only used with Q. For S, we name its unit volt ampere, or we call it volt ampere. So these are units. So what are the units we use for the different types of powers? We use volt ampere for S, we use VAR for Q, and we use watt for P, or the active component. So if we say we have a load of 10 kW, so what is given for this load? What you are given for this load? This means that its P is 10,000 watts. Now if you have a load of 5 kVA, so what is the meaning of this? The meaning of this is your S as magnitude equal 5,000 volt ampere. So from the unit, you will know if the given power is active, reactive, or complex or apparent, as we will see later on. Okay? Clear up to this point? So this is the third equation we have for the complex power. Okay, clear up to this point? Okay, so let's move forward. Now we have the following. We have P equal VI cos phi. We have Q equal to VI sin phi. Don't forget, I will write down VI sin phi, and I'm assuming that you understand that Q is a scalar, so V and I are magnitudes. And I'm assuming that you understand that P is a scalar, so V and I are magnitudes. And we have S vector equal to P plus JQ. Now we can represent this into phasors. So we can say we have P in x-axis, and we are adding Q with 90 degree, and the total here, this vector here, is S vector, and we call this the power triangle. So the power triangle is a triangle that represents the relation between the different types of powers we have. So we have P horizontal or real, and then we add JQ or Q with 90 degree, so we can get S complex. Now, what is this angle here? So I will give you a second to think about what is this angle here. What is this angle here? Any idea? So this angle here, let's name this angle as X. So you know that tan X, tan this angle X, equal to Q over P. So tan this angle X equal to Q over P, equal to Q is VI sin phi, P is VI cos phi. So V cancel V, I cancel the I, so this equals to tan phi, which means that your X is actually phi. So we can remove X from here, and we can write this angle as phi. So the angle phi is the angle in the power triangle. So we can write down that S vector equal to a magnitude, which we will name it magnitude S, and an angle phi. So the magnitude of S, the length of S vector, we name this the apparent power. Okay? So the magnitude of S, we call it the apparent power, and phi is still the phase angle. So phi is still named as the phase angle, which is theta V as we defined minus theta I. So here we defined a new power, and we name this power as the apparent power, and the apparent power is a scalar, and it is the magnitude of S, and its unit is volt ampere. Okay? So if we need to write an expression for magnitude S, what is the expression for magnitude S? What is the expression for the apparent power? So can you give me an expression for the apparent power? So the apparent power is magnitude S vector, and S vector equal to P plus JQ. So its magnitude will be square root P square plus Q square. So when you square P, you will have V square I square cos square phi. When you square Q, you will have V square I square sin square phi. So if you take V square I square as a common factor, you will have sin square plus cos square, which is 1. So we can write this as VI, and its unit is volt ampere. And that's why we call it apparent. Okay, so if you have a load, okay, so this is a load, say this is a motor, okay, and on the motor it is written that this motor is 120 volt, 6 ampere, whatever the information here. We call this the nameplate. So on the nameplate, which is a piece of metal attached to the equipment you have, and on this piece of metal they will write down all the basic information for this equipment. So on this motor, on the nameplate of the motor, it is written that this motor is 120 volt, 6 ampere, which means if you took this motor and you plugged it into 120 volt and you are loading this motor to its rated, it will be 6 ampere. Okay, again, what is the meaning of this? What is the meaning of rated? So if you have a motor and this motor is 5 horsepower, we call this the rated. So the maximum load that we can throw onto this motor is 5 horsepower. So if we say this motor is 5 horsepower, so if we take this motor out of the box and we connected it to 120 volt and we put a load, we start to load the motor with 5 horsepower, which is written on the nameplate, it will take 6 ampere. Now if I'm asking you, what is the power of this motor? You will say, okay, it's 120 volt, 6 ampere. So the power is 120 volt multiplied by 6 ampere. This is the power. Which power is this power you are calculating, VI? Is it the active power? Is it the reactive power? Is it the complex power? Is it the apparent power? So you multiplied VI and it is only magnitudes. So it is not the complex power, because the complex power we need an angle. And it is not the active component, because the active component is VI cos phi, so we need phi. And it is not the reactive component, because the reactive component is VI sin phi. So what you will get by multiplying V and I, you will get the apparent power. This is the apparent power. This is what will be logical for you to calculate the power by just multiplying V and I. That's why we call it the apparent. So if you multiply V and I, this is the apparent power. This is the logical power that you can get. So the apparent power, or magnitude S, is VI in RMS. Again, we are going through every single equation that we can use in AC circuits. Don't get worried with the many formulas that we are using, because at the end you will have a formula sheet, but I need you to understand how we got these equations and how we can use it. Okay, let's go back to S vector. So S vector equal to magnitude S and angle phi. So what is magnitude S? It's a V magnitude, I magnitude, which we named this as apparent power. Don't forget that the apparent power is a scalar. And the angle, what is the angle phi? So the angle phi is the angle of voltage minus the angle of current. Now here's a question. If you have V vector equal magnitude V, angle theta V, and you have I vector equal magnitude I, angle theta I, write down an expression for S vector. Okay, so I will give you 30 seconds to answer this. So if we say that we have a voltage V equal to a magnitude and angle theta V, and we have a current I which equal to a magnitude and angle theta I, can you get an expression for S vector? So what is S vector? It's a magnitude V, magnitude I, angle theta V minus theta I, which is the equation we have here. So can we say that S vector equal to V vector I vector? Or what is the mistake here? If we say that S equal to V vector I vector, the multiplication of two vectors, you multiply the magnitudes and you add the angles. So this will give us magnitude V magnitude I with an angle theta V plus theta I. And this is not correct. Why? We need the angle to be negative while the angle here is positive. So how we can make this correct? How we can make the angles to be subtracted, not added, by writing S equal to V I conjugate. And conjugate means you reverse the angle of the current I. If you write S equal to VI conjugate, so I conjugate is I with an angle negative theta I. So I conjugate equal to magnitude I, and its angle is negative theta I. So when you multiply VI conjugate, you will get S vector. So S vector, or the complex power, equals to VI conjugate in vector form, okay, or in phasor form. Let's take an example. So we have a load with V equal to 100 angle 3 degree, and I equal to 5 angle negative 17 degree ampere volt. Now can you calculate P? So how we can calculate P? We take magnitude V, which is 100, multiplied by magnitude I, which is 5. Then we will multiply it by cos the angle of V, which is 3, minus the angle of I, which is minus 17. So phi equal to the angle of V minus the angle of I equal to 3 minus 17 equal to 20 degrees. So P equal to 100 multiplied by 5 multiplied by cos 20, or equal to 500 cos 20. And its unit is what? To calculate Q, it will be the same exact form, but we will use sine 20 instead of cos 20. And its unit will be var. To get S, the apparent power, it will be 500. It will be magnitude V multiplied by magnitude I. To get S complex, it will be the 500, its a magnitude, and its angle is phi, is 20 degree. So the magnitude for S is 500, it's VI, and its angle is phi. And the unit for S is volt ampere. Okay? Or, let's do this in the second page. Or, we can say that S equal to V I conjugate equal to V is 100 angle 3. I conjugate is 5 angle positive 17. Why positive? Because I has an angle negative 17, so its a conjugate will be positive 17, which will give me S equal to 500 angle 20 degree, which is the same exact answer. Now if you take this S and you write it from polar, you write it into rectangular, S rectangular, it will be 500 cos 20 plus J 500 sine 20. This is the conversion from polar to rectangular. So what will be the first term here? So this first term is, here is P. And this second term here is Q. And this is what I prefer to do. Okay, whenever I need to calculate power, this is what I will do. So I will, step 1, I will calculate S as a V I conjugate. Step 2, I will put this result into rectangular, which will give me P plus JQ. Okay, so when you do this, you will get S vector, you will get apparent power because it's the magnitude of S vector, you will get P and Q, all of them in just 2 steps. Okay, so how to calculate power? This is how I calculate power. I start by saying S equal VI conjugate, and once I have S as VI conjugate, I put it into rectangular form, and after I put it into rectangular form, now I have P and I have Q. Okay? Is this clear up to this point? Okay. Now let's define power factor. Okay, so if you have a motor here and you are observing what is the power going into this motor versus time, so you will see something like this. The question is, do you actually care about the shape of the power, or you care about what will be the mechanical power coming out from the motor? So what you will care about is what is the mechanical power, how much energy is converted from electrical to mechanical, and it will be the output. Okay, so this is what we care about, the amount of energy that is converted from electrical to mechanical as an output in the motor. Now, if you observe this wave, can you determine how much power or how much energy from this wave is converted to mechanical? Yes. How? By finding the active component of this wave, because the active component represents the power that will be converted from electric to non-electric, and it will be productive. So from this power, we are caring only about P, the active component. Now, if this motor takes 120 volt ampere, okay, but P equal to 24 watt. So this motor has an apparent power you will see. So say this motor is 100 volt, 1.2 ampere. So when you multiply 100 volt by 1.2 ampere, it's 120 volt ampere. This is the apparent power. Okay? But the active component that you will see from the motor is just 24 watt, which is 20%. So 20% of the apparent power, the power you will see on the motor, just 20% are productive, are active. So is it a good motor or bad motor? So this factor here, the ratio between P and magnitude S, is very important, because this factor here, P over magnitude S, is giving you the portion of the power apparent in relative to the productive, or giving you the productive component in relative to the apparent power. So this ratio P over magnitude S will give you what is the portion of this apparent power taken by the motor, the power you see that the motor is taking, what is the percentage of this power is actually productive, and you will see it as a mechanical output. So we name this ratio as power factor. So the power factor is the portion of the power that is productive relative to the apparent power. So if you have two motors, one motor with power factor 0.7 and one motor with power factor 0.9, what does this mean? That's the 0.9, 90% of the apparent power it takes will be converted into mechanical. It will be productive. What about the 10% will be going back and forth between the motor and the supply? So the motor will take this energy from the supply and store it, then it will return it to the supply. Some students will say, okay, the reactive power is useless. Why we just not get rid of it? When we learn the magnetics, we will understand that this reactive power is essential in doing the energy conversion. It's like the water coolant you have in your car. So the water coolant amount, or the volume of the water coolant you have in the radiator is the same, it's not changing. But it acts as an energy exchanger, so, or heat exchanging. This is the same as the reactive power. It will be the facilitator for the energy conversion, so you cannot get rid of it, as we will study in magnetics. So the power factor equal P over S. So P is VI cos phi, magnitude S is VI. So here VI will cancel VI, so the power factor is actually cos phi. Okay, and this is one of the important equations we have, that the power factor equal to cos phi. So I will stop the lecture here, and we will continue the second part of the lecture.